Hello and Assalamualaikum everyone. Our Group 2, will be presenting about flatness inspection feature of piston. Moving on to our team members, Muhammad Iqmal Hakimi, Nur Farah Amira, I, Nur Shazwana, and the last one, Nurul Alia Shafika.
This our content for this presentation: introduction, CAD drawing design, design for manufacturing concurrent cost, design for assembly, result and discussion, and the last one we got conclusion. In modern manufacturing, efficiency, quality, and cost effectiveness are crucial, especially in designing precision tools like jigs and fixtures. Applying design for manufacture, DFM, and design for assembly, DFE, helps simplify product design, reduce manufacturing and assembly costs, minimize errors, and improve product quality. This project applies the FMA tools to improve the existing flatness inspection feature for an aircraft piston designed during the jig and fixture design course. Although the current design works, opportunities exist to optimize it using the FMA software. Let's break down all the objective. The first one got assess current manufacturing and some assembly method. Use DFM or DFA tools to analyze design and estimate costs. Identify design improvement for better efficiency. Apply DFMA software to solve practical engineering challenges. The last one we got strengthen understanding of DFMA in real world application. Next, we got the technical drawings. On the left, we got the base plate, clamping mechanism on the right. When both of the parts are combined together, then an inspection feature is made. This is our exploded assembly drawing for a flatness inspection feature used to check the piston surface. The assembly consists of two main parts. The first one we got a base plate, which supports the piston, and the second one we got a clamping mechanism to hold it in place during inspection.
Design of the feature current costs aims to simplify reduce costs and enhance the content by designing parts related to the manufacturing processes. We use software to use artificial intelligence and both components are made of generic stainless steel via semi-automatic semi-tester as the process for medium for the material we use is generic stainless steel selected for corrosion resistance, strength, and compatibility with stainless. For the process, we use the semi-automatic SEM testing balance cost and efficiency ideal for lower volume parts with moderate complexity. DFM concurring cost. This is the cost summary for the fixed group and product line. And then this is the cost summary for the clamping mechanism. Shown the product type volume species parts. To analysis the cost summary display, material and process costs such as potential for design optimization to reduce raw material usage and complexity. For the summary, clamping mechanism. It analyzes the higher tooling and setup costs due to complex design. The material usage is efficient, but part could benefit from simplification. To summarize, and recommendation from the concurrent cost, both components incur higher costs due to production volume and tooling or setup expenses. For base plate, it should be optimized the design to reduce the material waste. For clamping mechanism, simplify the design to reduce the tooling or setup time. Overall, increase batch size, explore the alternate processes, and apply the FM principle early to lower costs. This is the design for concurrent cost. Is
Hello everyone. Now I will present our design for assembly or DFA. DFA is a structure used to improve how easily and cost effectively a product can be assembled. The main goal are to reduce part count, simplify handling and orientation, and improve fastening method. We use DFA software to analyze the part, assembly time, and production cost to identify opportunity for improvement. In our assessment, we review each component impact on assembly. We found that while the total number of parts are minimized, there was still challenging with handling, orientation, and fastening that increase assembly time and complexity. We also consider ease of disassembly, which is important for maintenance and recycling. The current design does not include clear strategy for disassembly, which could make servicing more difficult. To address this, we recommend adding quick release feature, arranging parts so they can be removed in a logical order, and using label or visual cue to guide this assembly. The DFA results show a low efficiency score with a DFA index of 12.4 and an assembly time of about 95 seconds per unit. Most of the cost, around 97%, come from a part rather than labor, but improving assembly could still reduce error and save time. In a summary, the design has strengths such as low part count but need improvement in assembly efficiency and disassembly planning. Moving forward, we suggest simplifying fastening, improving alignment, and integrating more function into fewer parts. This change will help create a more efficient, cost-effective, and sustainability product. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ikmal Hakimi bin Muhammad Zarizam. My number matric is AG230022. So I want to talk about result and discussion, component functionality and integration, feature composition, two key components, base plate and clamping mechanism, designed to ensure secure, repeatable piston positioning. Base plate material the material that we use is rigid steel. The dimension is 180 mm times 240 mm times 20 mm. Featured pre-drill holes, corrosion resistant surface. Clamping mechanism. Material that we use hardened stainless steel, quick release clamp with rubber coated jaws, protect pistons surface, and also adjustable for various piston diameters. On top of that, design note, the modular integration for easy assembly and functional but show cost and assembly inefficiencies. Next, the FM cost analysis. We use Bootstrap software production scenario. The process is semi-automatic sand casting. The volume is 50 unit. Batch size is 10. Every batch size. So for base plate cost breakdown, total unit cost is 177 ringgit 74 cents. So every piece part is 117 ringgit and 74 cents. For material, we use 41 ringgit and 47 cents. For the whole process, we use 68.99 cents. So for the tooling or per unit, the cost is 60 ringgit, and for the reject cost is 90 cent, 9 cent. So low material is used, but complex tooling is increase the cost. So for the key insight, low production volume, equal height per unit cost. Recommend for the recommended exploring alternate process, that is CNC or 3D printing. For identify issue, no self-locating feature, require precise alignment, and also lacks foolproofing like asymmetric design and orientation guide. So increase assembly time and error rate. Thank you so much. For the second part of result and discussion, I will talk about design for assembly, DFA. So the DFA evaluation metric for this project, the FA index is 12.4. The assembly time that for every piece is 94.65 seconds per unit. So every piece cost, as I said, is 170 ringgit and 82 cents. For the labor cost is 3 ringgit and 82 cents. So minimum of part that achieved is 2. Identify issue that we found is no self-allocated feature, require precise alignment, lack foolproofing, and also increase assembly time and error rate. Assembly and lifecycle design. Current limitation: no tool-free assembly, no visual or modular cues, and also the assembly may damage the components. Improve opportunities that we need to apply on our project is add quick release fasten, include color coded or number indicator, use clips, thumb screw or tool free latches. This is for the support for easier maintenance, calibration and recycling. For the next opportunities for optimization, first for the material and geometry, reduce base plate mass, use ribs or lightweight material, so switch to aluminium or polymer for less critical loads. Secondly, process selection, replace sand casting with CNC or 3D printing. Also we use investment casting. For the assembly enhancements, self-align impacts, dowel pins, snap fix or clip-on design, standardize hardware to reduce part variance. Thank you. For the last part of the result and discussion, summary of the key findings. First, functional success, support various piston sizes, modular and sturdy design. So we have identified the inefficiency, high material and tooling costs, assembly lacks ergonomic feature, poor disassembly design. Recommended improvement: we reduce the material that we use and the part that have complexity, switch to efficient manufacturing processes, add feature to each assembly and disassembly. This is for make the feature cost effective, scalable and maintenance friendly for future production. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hikmah Hakimi bin Muhammad Zahir Issa. My metric number is AD230022. So I want to talk about the conclusion of this project. So first, functional achievement, feature meets its core purpose. It's stable, it has a rigid base for inspection, adjustable clamping for various piston sizes, protect surface integrity, rubber coated jaws and quick release clamp. We use robust material, hardened stainless steel and structural steel. We designed it with user convenience and mechanical integrity in mind. So we have identified the challenges, the FM and the FA inside. High per unit cost from small batch production, complex tooling, 4,000 ringgit for clamp. This is quite high for a clamp. Time intensive process such as sandcasting and finishing. Like we identified, we should use 3D printing. We will cost effective. So low index 12.4 due to manual handling and orientation difficulty. Next, less of circuiting and modular feature and longer assembly time. That is 94.65 seconds per unit. So the opportunity for improvement. For material optimization, we use lighter alloys or structural polymer. Apply with piping or cut out to reduce weight. Manufacturing simplification. Switch to CNC machining or additive manufacturing. We simplify mold design to reduce tooling costs. And for the assembly and maintenance, add self-aligning feature and snap fits. Include tool-free quick release component and also support assembly with a visual indicator. So the final thought, the current design is functionally strong, but it is costly and inefficient to produce and assemble at a low volumes. The FM and the FA analysis highlight area for the targeted improvement. Applying these strategies will make the feature more cost efficient, easy to assemble and maintain, scalable for mass production or automation. With thoughtful refinement, this feature can evolve into a high-performance, commercially viable tool for piston inspection in industrial application. Thank you so much.
Thanks for watching, guys.